Alright, so at the end of the first video I asked you, based on the precipitation shown over the last 10 days here, what would happen to the discharge, what that would look like if we graphed it, and the same with gauge height. So, um, so what does that mean? So a lot of streams have these USGS monitors. Lucky for us, there's a website. It's a bit of an antiquated website, but we can go there and get data, and you can see these as you drive around your various sections of streams. And so it's doing the same thing that we would do on the field trip, going out and calculating discharge. And so you can see that that's what this is doing, gathering some other data as well. And so we have this data readily available, and that's what we'll be looking at. All right, so we see it here. Here's our discharge. Again, we saw this spike in precipitation on April 24th. And so here the discharge is increasing, right? So you would expect that to happen. And then if the discharge is increasing, you would also expect the gauge height to increase. So gauge height is, again, just the height you can see in the picture on the left. Often near bridges, you see scales like this to measure gauge height. And people in the area know this very well because they know what that means for their home if they are near the water, or likelihood of nearby roads and other businesses being flooded. All right. So again, same thing with this gauge house near streams. All right, so here, coming back to the data for now gauge height, you can see the same thing that is happening, same kind of overall graph. The precipitation increased on the 24th. You saw the discharge increase for the same time period, and going along with that is gauge height. So gauge height and discharge are related, right? And so as you walk through the second part of the lab in the investigation manual, really what we're doing is just using these different graphs that we can create to find the relationship of this, right? So if we know the discharge, we can determine gauge height. If we know gauge height, we can determine discharge. All right. Once you get discharge, then you can get a graph to look at the recurrence interval. Now, for us, I didn't go through for our lab how it is you do that. But looking at historical data, we can put together a graph like this. It's a bit of an onerous process, so I didn't have you do that, but I did present the graph. Again, going back to the USGS website, we have a lot of historical data for these streams, and so we can create these graphs from that historical data. We can also extrapolate into the future for larger events that haven't occurred yet, right? So if the largest flooding event that has occurred would be something like a 10-year flood, and that's what this recurrence interval means, is a 10-year flood here and a 100-year flood. So if the largest had been a 10-year, then we would sort of extrapolate out into what this looks like based on the curve that you see here. All right, so that's what we're looking at here, is the recurrence interval. Right? So this should intuitively make sense. If the discharge is, pretty low, pretty close to what it is on a daily basis, the likelihood of having a flood, or not really a flood, but the water being that height, is every year, right? That's what it is. Every year, it's pretty much that height. As the height increases a little bit, then the probability, maybe it's just barely overflowing the banks, then maybe that happens every 1.5 years, every 1.25 year. But if we get to some significant increases in discharge, right, true flooding events, then the recurrence interval starts to increase. Right? And then if we get into things that are like at city flooding, those are really, really massive amounts of water moving by. And so the discharge increases, and then we get into a recurrence interval of something that's not very likely. It happens, or is expected to happen, infrequently. All right, and so we see this illustrated in a couple of ways. As we move away from the channel of the stream up onto the floodplain, the further away we move from the stream channel, the less likely that area to be flooded. That's why we have zoning laws, right? We don't permit people to build certain structures near water because we know that they're going to be flooded, right? It would be a very unwise decision to build something that is going to be flooded every 2 years, right? Your insurance wouldn't let you do that. They wouldn't pay you if you got flooded because you built in a floodplain. All right. Historically, though, we have relied on water for a lot of things. And so we do have a lot of, like in Ellicott City, we do have a lot of cities, we do have a lot of businesses and industries that have built near water that, if we were to do it all over again, maybe they wouldn't be built where they are. Same with some vacation spots built closer to water than maybe they should be if we were to build there now. But at any rate, as we move further away, the likelihood of a flood, the chance decreases, right? If you're closer to water, then obviously if you're right on this little section here where I'm pointing, the likelihood's like 100%, right? Every year the water's going to be about that high. As we move further and further away, then we get into a very unlikely case where there's a 1% chance, a low probability, and that would be a 100-year flood. If we move even further away, then we get into the 1,000-year flood. All right, so here we have that same kind of chart. So we have their discharge and we have the return period here. And again, as I said, if we don't have all that data, we have the historical data and we can extrapolate out what that might look like. Again, the probability here just shown in terms of not numbers, but high versus low. The low probability of the return periods, when they're larger, there's a lower probability of flood. All right, and so for that reason, we have different zoning. And so here you see that we have a river, and then what these areas would be zoned for as we move further away. We have things that aren't going to be severely impacted if flooding were to occur. So nothing really built right near the river. We might have pastures or ball fields or parks and things of that nature. Roads cause some little bit of damage, but not much. And then we get into industry and things of that nature. And then finally, homes built furthest away. Again, shown on the picture of the right, further away we move from the stream channel, the greater the recurrence interval, and the less likely the flooding. Right, and then here you can see as you move further and further away, the cost savings that would be in terms of that you're going to be flooded. The closer you are to the floodplain, the further away, the less likelihood, and that is going to be your best bet. All right, so again, zoning laws sort of prohibit that. All right, and then finally what we wanted to look at is probability, and there's a couple of different ways to do that. We can do that with the equation, but the way that we have it in the lab manual is just looking at another graph. And again, there's a relationship between probability and recurrence interval. You see that here, and discharge. So that's really sort of what you're doing, is going through these different steps, looking at the different graphs to get numbers to calculate the probability. And again, that's all it is the probability, right? And so when we say that the Ellicott City flood is a 1,000-year flood, a lot of people on social media that I saw were not really comprehending what that means, right? So what that really just means is that the discharge was really high. It was unexpectedly high, something that we would expect about once every 1,000 years, but that doesn't mean that it's going to happen every 1,000 years. And so it just so happened for Ellicott City that in a span of 2 years, there were massive flooding events that had a pretty extreme amount of discharge for that area, which resulted in very, very bad flooding. All right, so I think we've seen this enough times. You probably got it, but here we have the city of Houston. Again, a lot of areas have calculated these floodplain areas and have zoning regulations now in place. There are some ways around that as you move into places near the water. Ocean City, you'll see it there. Structures built so that they're essentially up on stilts with the parking underneath. And so those zoning laws vary from place to place. You don't tend to see too many structures like that in this area. However, where I live up in Bel Air here, there is there is an area near a floodplain behind Bel Air High School that I never thought they would build in, and then a few years after taking my students out to look at the stream there, they started to build there. And what they did is put in a business. So there's a bunch of, I'm not sure what else in there. I know there's a couple doctor's offices, but it's essentially up on stilts. So the parking is underneath, and all of the plumbing and electricity is up on the second tier with the first layer of offices. And so they essentially did build that up on stilts, but that's kind of rare for something that you would see in this area. Most of that you see near the beaches. All right, so more risks if you're into looking at these kinds of things. Here we have the years in the floodplain and the risks. So if you were to buy a house near water, and here we have something either along a stream or near the ocean, the longer you live in that building, that's why I said earlier it's a short-term investment. The longer you live there, the greater the likelihood of being flooded is. Right? And so if you build a place near water and you live there for 5 years, the risk is lower than if you live there for 30 years, right? Because of the recurrence interval. Right? And then the same is true with how far away you are from the stream in this case. 10-year flood, 50-year flood, 100-year flood. So you can see the likelihood or the probability decreases. Right? Especially once you get into something like a 500-year flood, a very rare instance. But still, as you go down over time, the risk increases. Okay, so at this point, you should do the remainder of the lab on page 32, 33. So that is questions 6 through 11.